Okay, so all those times you were sitting in math class and you said to your teacher, or you said to yourself, why do we have to learn this? I'm never going to use it. Well, here's the answer to your question. This is why you had to learn all of that fun stuff. You are going to get to apply trig to forensic science. Woohoo! Now, if you're freaking out because you were never very good at trig or you didn't really get the trig or anything like that, don't freak out. It's okay. I'm going to walk you through it. I'm going to make it pretty easy to plug and chug your way through this. You should be just fine this unit. So hold on to your bootstraps because we're going to get started. Now, you're going to hear me say the word trajectory a lot. And trajectory sounds like a fancy word, but it's really not that fancy. All it means is we're talking about the path a bullet took. And if we can figure out the path a bullet took, there's a lot of other stuff we can figure out. Fortunately, what we have is this handy math called trigonometry that many of us have a bad attitude about, but really don't need to because it's really not that bad. And if you can remember that good old SOHCAHTOA that you learned when you were in trig class, you are going to be just fine. And in fact, you don't even need to remember all of SOHCAHTOA because we are mainly going to be using one section of it. So we're all good. Trajectories, we're just figuring out where a bullet went, where a bullet came from. We're going to use trig to do it. Okay, so first things first, because this is an introductory forensic science class and you guys are just learning this stuff for the first time, we're going to assume that all of our bullets hit walls. Now, of course, every bullet that's ever shot does not hit a wall, but to make things easier and simplify things for us, we're going to say bullets hit a wall. So there are three important measurements when we're looking at bullet trajectories or paths that bullets take, and one of them is the angle of impact. So if this is our wall, our question that we're going to ask ourselves is, what angle did the bullet hit the wall? Now, it's possible the bullet came in and hit the wall at this angle, or it's possible the bullet came in and hit this angle, or even this angle. So we need to know, first of all, what was the angle of impact of the bullet. The next thing we want to know is how tall was the shooter. And then the third thing is, what was the distance of the shooter from the wall or wherever the bullet hit if it wasn't the wall. So angle of impact, height of the shooter, and distance of the shooter from the wall are the three important measurements that we're always going to be talking about. You know from algebra that if you have an equation with, let's say, three variables in it, let's say you've got x plus y equals z, and I give you two of those, so I take two of those away as unknowns and I make them knowns. Let's say I put in 8 for x and I leave y as y and I make z 10. You can figure out what y is if you need to. This works the same way. If you know two of those three measurements I was just talking to you about, you can figure out whatever the missing value is. If you're standing at a crime scene, you're going to have a bullet hole in a wall if you're even bothering to do a bullet trajectory. If you don't have a bullet hole in the wall, doing a bullet trajectory is a pointless thing. So with the hole in the wall, and I'm going to talk to you about this later, you're going to have the angle of impact. So that is one thing that we generally assume that we're going to have, is the angle of impact. And sometimes we'll abbreviate that as AOI, angle of impact. So if we have the angle of impact and we have the height of the shooter, then we're going to be able to figure out where the shooter was standing for the crime scene reconstruction. If we have the angle of impact and we have some kind of footprints or maybe the cartridge casings that fell out, we can perhaps determine the height of the shooter. So with two of these things, an angle of impact is probably going to be one of them, we can figure out what the third thing is. So for the purposes of calculating trajectories, the height of the shooter is going to be calculated as shoulder height. So if we're looking at this woman shooting, the height that we're using as the height of the shooter is actually going to be this distance here, because if you take a look at the path that the bullet would take, or the bullet's trajectory from the bullet or from the gun out, the bullet came out at the end of the gun here, but followed this path along the gun and also along her shoulder. So it's okay to extend that trajectory back. And when we talk about the height of the shooter, we're talking about shoulder height. So that's important to remember, because we do then have this distance that's unaccounted for that we have to kind of average out, where we're thinking about, okay, how tall is this person? How much head does that person have on top of their body that's adding to their height? And that's going to leave a little bit of variability that we need to think about. We'll talk about the less useful situation first, which is if a bullet is fired straight into a wall. Now, this slide didn't import very well into explain everything, but it is what it is. So the angle of impact of a bullet that's fired straight into a wall is 90 degrees. Because if we have our wall here and we have our gun here and the bullet goes straight into the wall, then we have a 90-degree angle right here. So the angle of impact is 90 degrees, and the hole in the wall is going to be perfectly circular. That's the word that's missing there. The hole in the wall is going to be perfectly circular. So we're going to have an absolutely perfect circle if that angle of impact is 90 degrees. Now, this is not an entirely useless situation because the hole will help determine the caliber of the gun and the type of gun that we're looking for. Remember that the caliber of the gun tells us how big the bullet is in diameter and how big the gun barrel is in diameter. So by measuring simply across the hole, we can figure out what the caliber of the gun is. Now, this hole is not going to help us determine the distance of the shooter from the wall or the shoulder height of the shooter because we don't have an angle of impact that's going to work with our trigonometry. A 90-degree angle of impact will not work. All we know now is the caliber of the gun. But if the angle is off by even the teensiest bit, the hole in the wall is going to be elliptical. So we're going to get some that are big ellipses and some that are smaller ellipses, depending on the angle of impact. The smaller the angle of impact, the more elongated the ellipse. What that means is that if I've got my wall here and a bullet comes in here, I'm going to end up with a really super stretched out angle of impact. But if I have a different situation, where I have my wall here and the bullet comes in here at this angle, so I'm talking this angle of impact now, then I'm going to have a shorter, fatter ellipse. Now that hole is going to help determine the size of the bullet still, but now it can also help determine where it came from or the height of the shooter, because we can still measure across that ellipse to find out what the width of the bullet was that came in. So we can still figure out the caliber of the bullet. So with a bullet hole in the wall, we can generally figure out the caliber of the bullet and therefore the caliber of the gun. We'll start with angle of impact because that's the easiest thing to deal with. There are two ways we can find the angle of impact. One of them is if you have a dowel rod that's the same size as the bullet. You just take that dowel rod, like the one that we have right here, and you put that dowel rod into the bullet hole, and it will slide in at whatever the angle is, and it might go in, it might go all the way through. In this case, the dowel rod goes all the way through. And you can see the path right here of what the angle of impact is. The other way you can determine angle of impact is mathematically. If you're going to use a dowel rod, the dowel could be wooden, could be plastic, it could be a laser if you're feeling fancy, and you're going to take a dowel that is the same size as the bullet and you're going to put it into the hole. The investigator is going to measure the angle formed between the dowel and the surface, probably using a protractor. The problem with this, though, is that as soon as you are putting that dowel rod into the hole, you could be destroying evidence. So any evidence that's in that bullet hole or around the bullet hole, anything like gunshot residue or fibers or DNA or blood, any kind of biological evidence, all of that's getting destroyed. So here we're going to discover how to use math to calculate the angle of impact, and we're going to discover something else that didn't import well into explain everything. So using math, we're going to look at our angle of impact, and we're going to measure two axes, the major axis, and major means bigger, so that's going to be our vertical axis. So we'll measure the major axis and the minor axis. Minor means smaller, that's going to be the horizontal of the bullet hole. So we've got the major axis and the minor axis, and then we're going to use trig, and you just need to learn this formula. This is just that easy. Learn this formula. So what this formula should actually say is that the sine of theta of impact is equal to the minor axis over the major axis. So the sine of theta is equal to the minor over the major. Now, you should be able to do this without my explaining anything, so I want you to stop this slideshow and I want you to actually make an attempt at doing this problem. Get yourself to an answer. Pretend it's a test. I know you haven't done it over and over and over again and it's your first time, but pretend it's a test and get yourself to an answer. Don't start this back up again until you have an answer on paper. Okay, so let's take a look. We know that the major axis is 20 millimeters. So here's our major axis, and that's 20 millimeters. And then we know that the minor axis is 15 millimeters. So we also know our equation, which we're always going to write down, sine of theta equals minor over major. And so the sine of theta is going to be equal to 15 over 20. We're going to do our math here, and so we know the sine of theta is going to be equal to 0.75. And now here's the important thing. You have to make sure that you have your calculator in degrees, not radians. Put your calculator in degrees, not radians. So sine of theta equals 0.75. So the inverse sine of theta, theta is the inverse sine of 0.75. So then when we kick that into our calculator, theta is equal to 48.59 degrees. If you didn't get that, go back and look at your work and figure out where you made the mistake. Don't move on until you know where you made the mistake. So in actuality, the more elliptical the hole, the more accurately the math will predict the angle. We're going to use both methods. We should use both methods to figure out the angle of impact. We're going to use the math first because that doesn't destroy any evidence. But once the evidence in the hole has been thoroughly cleaned out and taken and examined and all of that, then we can use a dowel rod. So if you use both methods, you can get a better confirmation, but you just want to make sure you do the math before you do the dowel rod and that you get all that evidence out of there before you put the dowel rod in. So once you have the impact angle firmly established, so you've done it using math and dowel rods, now you can actually figure out the path and do a physical reconstruction of the flight path of the bullet. And you'll use string to do that. And so you can start by taping the string to wherever the angle of it, wherever the point of impact is, extending the string along one side of the dowel, and then extending it further out, making sure you keep the angle the same, making a straight line down to the floor. And you know that the shooter's shoulder fell somewhere along that path. That doesn't mean the shooter's shoulder was on the floor. It just gives you the path between the floor and the angle to know that somewhere in there is where the shooter was standing. So here we have our shooter. I've put in a nice outdoor wall. I'm not sure why that outdoor wall is there, but it's there. And we have our bullet hole up here. And we know that the shooter's bullet left the gun. And remember, we have that nice angle going from the bullet to the gun to the shoulder. If you look really closely here, you can see a right triangle, but you have to look closely. From here, straight across to the wall, and then straight up the wall, we have a right triangle. And this is the right triangle that's going to make it possible for you to use for us to use our trigonometry to figure out these other pieces of information that we need. So in that triangle that we have, A is the vertical distance here, and that's going to be an indicator of the height of the shooter. Now that's not exactly the height of the shooter, but it's going to give us some information about the height of the shooter. Stand by for more information on that one later. The horizontal, B, is going to be the distance of the shooter from the wall. So the horizontal is going to be from our shooter's shoulder over to the wall. And that's going to tell us the distance the shooter was from wherever the bullet ended up. And then the hypotenuse, C, is going to be the distance traveled by the bullet. So it's going to say, we're going to assume that the distance of the bullet started at the shooter's shoulder, which we know it really didn't, but we don't have a nice right triangle if we started at the gun. So this gives us a triangle we can use, and that's just a representative distance anyway because it's all proportional. So let's look at an example because everything makes way more sense in math when you have actual numbers to put into your example. So we're going to start with a bullet hole that's found 100 inches from the floor, and the angle of impact is firmly established to be 55 degrees. So we know that this angle is 55 degrees. Ignore this weird little shape that didn't work here. So we've got 55 degrees there. We know that the shooter's shoulder is, if the bullet came and traveled along this path, then we know that this is where the shooter's shoulder had to be while they were shooting their gun. So this is the point where our shooter's shoulder was. We also know that a triangle adds up to 180 degrees. So if we have this as a 55-degree angle, and we know that this is a 90-degree angle, then the 180 minus this 55 minus this 90 is going to leave us with this third angle, which is 35 degrees. And that's the angle between the shooter's shoulder and the floor. So here's the shooter's shoulder angle and the floor. That angle is 35 degrees. But remember, knowing just the angle of impact isn't enough. We need more. So we have a suspect and we have a confession. We want to reconstruct the crime and find out where the suspect was standing when the crime occurred. So the suspect is 6 feet 5 inches tall, but that's the suspect's entire height. Since we have the suspect, we've gone ahead and measured and figured out the shoulder height, because remember, shoulder height is what's important. So we have a shoulder height of 69 inches here. But the bullet was found 100 inches from the floor. So here's the floor, here's the bullet. That total distance here is 100 inches. 69 of those inches were taken up by the person's shoulder height. So in order to figure out what this length is on the triangle, we have to subtract. So we just have to do 100 minus 69 to figure out that that is 31 inches on that side of the triangle. So now we have 31 inches on this side of the triangle, and we have two angles, so we have more than enough to figure out our one unknown, which is where the shooter was standing. So we want to figure out this distance of where the shooter was standing. Okay, so we have the angle, we have an adjacent side, we want the opposite side. So we're going to use tangent of theta is equal to opposite over adjacent. Remember, in the beginning I told you that you were really only going to use one part of that SOHCAHTOA. This is it. You're going to be using tangent most of the time. So you already know this distance is 31 inches. I don't know why it printed over here. 31 inches. And what you're looking for is this distance, and you have this angle. So you can go ahead and plug in tangent of 55 degrees is equal to the opposite, which is x, because that's opposite where the angle is, over the adjacent, and adjacent means next to, 31 inches. So the tangent of 55 times 31, because we cross multiply to get that out of the denominator, is equal to x. Again, make sure your calculator is in degrees mode, not radians, and you do the math. Tangent of 55 times 31, x is going to be equal to 44.27 inches, or if you take out 12 inches for every foot, x is equal to 3 feet 8 inches. So this is your final answer for where the shooter was standing compared to the wall. That's this distance right here that you just calculated. Okay, so I'm going to get this out of the way a little bit, make it a little smaller, get it out of the way so that I have some room to work. And we're going to start by drawing a picture, because that is the best thing to do to visualize and make sure you know what's going on here. So we have a bullet hole that's found 85 inches from the floor. So my bullet hole is up here, and that is a distance of 85 inches. The angle of impact is firmly established to be 65 degrees. Now, I'm drawing this like a flag for a reason. You'll see why in a second. Okay, so the angle of impact is firmly established to be 65 degrees. A footprint is found 6 feet 3 inches from the wall. So I'm going to put my shooter in here, because remember, my shooter's arm needs to fall somewhere on the trajectory of the bullet. But my shooter's footprint was found right here, which is 6 feet 3 inches from the wall. Now, here's the first problem. 6 feet 3 inches is not something I can plug into my calculator. It's not something that's going to work for me. So I need to go ahead and change this into just a straight number of inches. So I have to do 6 times 12, because there are 12 inches in a foot. 6 times 12 plus 3 is going to give me 75 inches. So this distance is 75 inches. That means that this distance is 75 inches. So if I know this distance is 75 inches, I need to figure out what the portion that is going to help me figure out the person's height is. So I can't use trig to figure out this distance. There's nothing that's going to work to help me figure out that distance. But what I can use trig to figure out is this distance. So right now I'm just going to focus on this distance. So I'm going to make this my unknown. So I'll start with tangent, because tangent is the way to go. So the tangent of 65 degrees is equal to opposite, so I'm going to look opposite, 75 inches over adjacent. Adjacent means next to, but that's my unknown here. So I have now my unknown times the tangent of 65 is equal to 75. I'm going to divide both sides by the tangent of 65 so that I end up with x equals 75 over the tangent of 65. And when I do the math, again, making sure that my calculator is in degrees, not radians, I'm going to get x equals 75 over 2.14, which is going to give me 35 inches. Yay, my shooter's 35 inches tall. No, my shooter's not 35 inches tall. That was that distance marked x. This distance right here is 35 inches. I still need to go back and figure out what my shooter's height is. And my shooter's height is this distance. So I need to take the 85-inch total distance minus the 35 inches between the shooter and the bullet hole to get the actual height of the shooter, which is 50 inches. So that's a 50-inch shoulder height. So this distance is 50 inches. So the shoulder height of my shooter is 50 inches or 4 feet 2 inches. Now that probably seems pretty short to you, but remember that's a shoulder height. You've got another 8 to 10 inches of head stuck on top of that person's body. So it is a fairly short person, but not an unreasonably short person. So this is your final answer here. All right, I hope that was fun. You're going to have lots more practice with this in the lab and on homework. This is something you absolutely have to be able to do. It's one of the biggest parts of this unit. So go back, look at your notes, go through this bunches and bunches and bunches of times until you completely understand this.